face is so close to the computer, I can see your acne.
Sorry. It's been very stressful, okay? Is that recording? Oh, yeah, okay, I guess. All right, we'll try it. Okay, so here we go. You're a jerk, Tiffany. Okay, hey, did you guys see, though, in the reading questions or the questions that you had to do yesterday, when you compare K and Q, when you compare K to Q, if K is greater than Q, so if the equilibrium constant is greater than the reaction quotient, did you guys find, would the reactants be favored or the products be favored?
Products.
Products, good. Okay, so the products get favored. So in other words, the reaction will shift to the right. If K is equal to Q, then that means it's at equilibrium, right? And then if K is less than Q, then the reactants get favored. So the reactants get favored, or in other words, it's going to shift back to the left. Okay, it's going to shift back to the left. All right. Now, having said all that, we are going to try some problems. I had posted some problems, and so I'm going to move, I'm going to see if I can pull those up, but they're on Classroom. So if I lose you, I'll try to bring it back. So give me just a second. But I'm going to go down here and see, I don't know, or is there a way to split my screen, I wonder?
There should.
You should be able to share your screen.
Just share.
Yeah, I don't think you can split it.
Okay, so share screen.
I don't know how our college algebra teacher does it, but she shares her screen.
Okay. Well, okay, so.
I don't know if she shares her screen. I don't know.
Okay. Well, can you guys see what I'm pulling up right now or no? Do you see that I'm on Classroom?
I don't see anything yet.
No.
Oh, you don't? Okay.
You'll probably just have to end up writing it on the board.
I see your face.
Oh, you still see? I'm sorry. Okay. Okay. All right. So, I don't know. Wish you guys were here. I don't know how to do that. But I'll tell you what. I'm going to go back to the board here, and then these problems, I'm going to do some practice problems, and I posted them on Classroom, okay? So if you want to go back and you want to look and see what the problems were, I posted these on Classroom. So I'm going to start, though, with sample problem, it's the one, I think it was the first one, it was practice problem equilibrium number 1. And it's 13.8 or something like that. And all that one was, because the other thing that it asked you about was equilibrium, the pressure constant, Kp. Kp is just the pressure constant. And you it's the same thing. You can find using gases, if you have partial pressures, you can use the Kp expression, but you write it the same way, okay? So you do products over reactants with all the same little rules, okay? But the one that I wanted to look at, though, for 13.8, so if you can see that sample problem, it gives you this equation. It's N2O4. N2O4, which is a gas, is at equilibrium, and it will break down to produce 2NO2 gas, okay? All right, now the thing is in the problem, it says, consider this experiment where this was placed in a flask and allowed to reach equilibrium, where the Kp is 0.133. So the Kp is 0.133, and it says at equilibrium, the pressure of N2O4 was found to be 2.71 atms. So I'm just going to write that here, 2.71 atms. Okay, and it says calculate the equilibrium pressure of NO2. Okay, so you're looking for the pressure of this one. So that's what we don't know. Well, if we know that you can use the Kp to write an equilibrium expression just like you can do it with Kc, let's go ahead and write this out. Let's write our equilibrium expression first. So Kp is going to be equal to, and the way that we're going to write this is the same way we did it for Kc, except this time we're just going to use normal round parentheses. And we're going to do products. And what do we do with that coefficient? Okay, we're going to make it an exponent, right? Divided by N2O4. Okay, so there's our expression. Now we just chug those numbers in there, okay? So we're going to put 0.133 is equal to, and I'm going to go up here and I'm going to find that this is what I'm looking for. So I'm going to say x squared over, and then I'm going to plug in my pressure, 2.71 ATMs. Okay. We doing okay? See where we got all of our numbers? All right.
Which number is this one?
So this one was, I think it was practice problem 1 on Classroom,
Practice problem 2.
or was it practice problem 2? But it's
number
type
2.
13.8. It's exercise 13.8. I don't know if it says that.
It's like the most recent thing you posted.
Yeah. So yeah, it was posted underneath all that other junk from.
There's like 5 million add-ons on it.
Yeah. So, hey, is Brody there?
Yeah.
Hello.
Hi, Brody.
Hey, Brody.
Good morning, Brody.
Good morning.
Good morning.
We've missed
We'll see
you.
how long my Wi-Fi lasts, but
Same,
I thought that.
hello.
Okay. So we're on problem. It's exercise 13.8, but it was on the most recent post, I think. But it practice problem 1 or 2, something like that. Anyways, and then you just solve for x. You're going to bring that up, and so you'll say x squared is equal to whatever that is multiplied together, like 0.360. And then we're going to, what do we do here? Square root it. Yeah, square root it.
I was about to say that. That's not fair.
The square root of x is equal to 0.600.
6 something.
Okay. 0.600 what though? What were we trying to find?
Atmospheres.
Atmosphere.
ATM.
ATM. All right. Good. All right. So that's how you're going to do that. That's a KC problem, you know, just like the way that you do KC problems. So now we're going to try another type of equilibrium problem. Okay. So the one I want us to look at now is this exercise 13.9, sample problem 13.9. And again, I don't know, I think it was practice problem, it was supposed to be practice problem 2, but it's the
Nope.
one, it says PCL5. That's the one we're looking for, PCL5.
I don't see a 13.9.
Uh-oh.
Is it the
yeah, I
first one?
don't see it either.
Okay, hang on just a second. I got to figure out which one. Which
I see
one are the-
13.7, 13.8, 13.10,
Oh, okay.
and 13.11.
So let's go ahead. Okay, so let's try out 13.7. So try the one that says 13.7. Okay, this is the one where you're trying to find the reactant dose of the Q. Okay, so problem 13.7, it says for the synthesis of ammonia, the equilibrium constant is 6.0 times 10 to the negative second. One thing that I think is a really good idea is just list out what you know, okay? So if it says the equilibrium constant, they're talking about Kc is 6.0 times 10 to the negative second. Okay, and this is at 5 degrees. It says predict the direction in which the system will shift in order to reach equilibrium in the following cases. So they give you all these different sets of conditions, and they're wanting to know is how does the Q compare to the Kc? Okay, and remember all those rules we wrote down at the very beginning, like if K is greater than Q, it's going to shift to the right. So that's what we're going to do. So let's try one of these out. If we do letter A, and I'm going to write the formula back up here. So Q plus H. Okay, if you've got all that, and
Dang, Brody, stop being so loud.
if you've got all that,
that-
NH3 is 1.0 times 10 to the negative third. That's the concentration. And I'm doing letter A, by the way. And then 1.0 times 10 to the negative fifth. That's the concentration of that one. And then I've got 2.0 times 10 to the negative third. So there's all those concentrations of those, okay? You would set up a normal Kc expression. You set up a normal equilibrium expression. So we're going to say, but remember, we're trying to find Q, though. You're trying to find the reaction quotient, and you set it up the same way. So I'm going to take...
Hey, there's kind of a glare on the board. What is the
Okay, so
concentration
the concentration of N2,
say for N2?
yeah, so N2 is 1.0 times 10 to the negative fifth. And then H2 is 2.0 times 10 to the negative third. Hey, Brody.
Hi, my camera finally worked.
All right. And then
Yeah.
1.0 times 10 to the negative third. I don't know. Would it help if I turn the front lights off? Let me see. Hold on.
I don't know. What sample problem was this?
Hey,
Yeah,
A?
it was 13.7.
yeah.
Okay, that's yeah. thank you.
Image, whichever one. Is the first one.
A?
Yeah.
That's a long problem. I don't know if I can do this.
Okay. All right. Any better? No, I still see glare. Oh, well. I tried. Okay. We're gonna
If anything, it's worse.
I can't even see half of those numbers anymore.
Oh, no.
Yeah.
When I turn the lights back on. Wait,
Sure.
Yeah.
Yeah, sorry. Like there's not a great way to do this. So I'm gonna just take that numbers and I'm gonna start plugging them in. I'm gonna put my products over my reactants. So I'm gonna say 1.0 squared divided by, I'm gonna take my reactants. Okay, I'm gonna say 1.0 to the negative fifth times 2.0 times 10 to the negative third, and then I'm going to cube that, right? I'm going to take that to the third power because of the coefficient right there. Okay. Now at this point, you just go in and solve it. You type it in your calculator, and you're going to find your value of Q. And so whenever you get that, it should be something along the lines of 1.3 times 10 to the 7th. .3 times 10 to the 7th. If you work that out, that should be somewhere in there. Now let me ask you this. If I want to know, if I ask you, okay, so at these conditions, would the products be favored? Is it going to shift to the right or is it going to shift to the left? How do you know?
Compared to the equilibrium constant.
Yeah, you have to take these two values. So you take the Kc value they gave you, which was 6.0 times 10 to the negative second, and you're going to compare it to the Q value, which is 1.3 times 10 to the 7th. Which one is bigger?
I kind of have a problem.
What's your problem? What's wrong?
Did you use
Yeah,
enough parentheses?
I agree. Yeah, I used right. me I got. Yeah.
You're cutting out really bad.
Yeah,
bad.
I can't hear you at all.
I call it robot speak.
You sound like Stephen Hawking.
Exactly.
Here's the right parentheses. I got 12,500,000.
That should be right.
Yeah.
That's right.
Yeah, 12 million.
5,000.
Oh, what? Like if you put it into exponent, like scientific notation, though, would it not be that?
Yeah.
It wouldn't?
I mean, yeah, I guess it would be, but it's still not 1.3.
It's close enough.
It's like 1.25.
Yeah, and I'm just going off the book value. Like last time when I got like 1.25, but they rounded it because of significant digits. So
Bleh.
yeah,
1.3.
but the main thing is though, how does this number compare to the KT? Well, K is
Much larger.
smaller. K is
Q
K
is
is
a
less.
lot larger.
Q is much bigger. And guys, for me, I have to always start with my K. Because if I don't, I'll get them confused. So I always start in terms of K. K at equilibrium is less than Q, which means that what side is going to get favored? If K is less than Q,
1 second.
Should
Reactants.
be the reactants.
the reactants. This reaction, if K
I forgot you pointed the.
is smaller than Q, this number right here, the reactants get favored. And that's a rule you're just going to have to remember. You need to write those things out and just try to remember it.
There was a easy thing to remember from the like website that you sent.
Yeah,
Follow the arrow and then reactants or products.
yeah. But the reactants are favored. So under these conditions, you would have more nitrogen and hydrogen gas than you would ammonia. Okay, it would shift back that direction. It's going to try to make more reactants. Okay, all right. So that's using Q. We've talked about K. We talked about KP is the same kind of value. It's an equilibrium constant. Okay, so now we're going to try that ICE formula. ICE,
Gross.
baby. Ding, 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 ding. Okay. So I'm going to look at problem. Was 13.10 in there? Can you guys find that one, 13.10?
It should be. Yeah, it's number 3.
It's number 3. Okay. So
Equilibrium 3.
yeah, we're looking at problem. It's practice problem 3, equilibrium 3 on Google Classroom. Okay. So if you want to read through that little problem, I'm going to read through it too, and I'm just going to start writing down my notes. Whenever you have one of these problems, I highly recommend that you just write down all of the things that you know about the problem. Start there, okay? So that's what I'm going to do, and you guys do it too.
Wait, which exercise problem is this?
It's called exercise 13.10. It's the one about carbon monoxide and water.
Okay, thank
Yeah,
you.
with steam, carbon monoxide. Okay. So carbon monoxide reacts with steam. Okay. All right.
Brody, mute yourself.
What is he watching? That's
not mine.
I don't know, but every
That's
time.
not
That might be mine.
Oh, I don't know. Every time someone talks, it
My brother's right next to me, so I think he's watching something.
nice.
like goes to their face. So I couldn't see what you were writing down. So all I could see was sitting there. Was Brody was just sitting there twirling his.
He's getting headphones. Everything's gonna be fixed.
If you click on
Yeah, I'm just sitting here watching TV.
That's funny.
thing, go like pin or screen.
Well, I wasn't going to say anything because at our house this week, like it has been a zoo. It's
You
I
should
was
see
not-
my
I was not meant to
my
home.
work table.
Yeah.
This
My work
this,
table is so
online
bad.
stuff stresses me out though. Like
What, doing the online stuff?
Yeah, it's kind of hard to get everything done.
Yeah, well, and that's what, like, me and Miss Bassing and Schaefer have all had this group text going. Like, number one, there's a reason why God did not make us homeschool moms. Like, I cannot do it. And
Yeah.
number two, like, the amount of work that is being sent home, holy crap. Like, do you guys listen? The assignments that I'm sending home, I'm trying to give you a full 2 days to do. So, like, I don't expect these things to be. And the assignment that I'm going to make today, there's a few problems every day that I want you to try to do, but it's not due all of it till Friday. Okay?
Okay.
Because, like, we are stressed out at our house. But, anyways. Okay. So having said that, though, so we know that our KC, our equilibrium constant for this 5.10. This, okay. All right. Now, tell me, it says calculate the equilibrium concentration. All of the species have 1 mole of each component, okay? So 1 mole component. So you've got this, 1 mole of this, 1 mole of this, 1 mole, and 1 mole. Okay. I'm going to erase that. Okay. All right. Now, first of all, before we go any further, we have got to figure out, these conditions are not at equilibrium, okay? So if they're not at equilibrium, we need to figure out how does the reaction quotient, based on what we have right now, how is Q going to compare to KC? Now, what was the KC again? If KC is 5.10, KC was 5, right? 5.10. We need to figure out our Q, our reaction quotient. Okay? So you're going to do this, again, the same way. You're just going to take all the concentrations, and they tell you that it's 1 mole per 1 liter. Guys, 1 mole per 1 liter just means it's a 1 molar concentration, okay? So all of these concentrations are just 1. So I'm going to set up my reaction quotient. So on top, I always put my products. So I'm going to put my 1 molar, 1 molar times this concentration, 1, divided by my reactants. I'm going to do the same thing. 1, this is the concentration of 1 because it's 1 mole per liter. 1 times 1. I don't have to put any kind of exponents up here because I don't have any coefficients, right? So I'm just calculating my Q. So guys, what is Q here? What would Q equal?
5.1.
And not KC.
Or, it'd just be 1.
1. It would just be 1.
Right? Okay.
Okay. So are you with me? Do you understand how I got my Q right here?
Mm-hmm.
I just took my concentrations of my products divided by my concentrations of my reactants, and I got Q. Now let's compare the KC value, the 5, to the Q value of 1. So what would you say? How does K relate to Q?
K is less than. Or,
Yeah.
K is greater than Q.
K is 5.
yeah. It's
Oh,
greater
K is 5. Yeah, K is greater than Q.
Yeah, K is greater than Q, right? So if you know that K is greater than Q, and this is going to be important later on, if K is greater than Q, which side would it shift?
The
Products.
It would shift to make more products. Now keep that in mind. You're going to try to make more products, okay? So we're going to try to make more products. So here we go. We're going to use something called the ICE formula. I like to call it RICE because that's how I learned it in college. For me, RICE is R-I-C-E. So on your paper, you're going to write, you've got the reaction written, and you write down the initial concentrations, okay? So initially in the container, they put 1 mole per liter container. So it's 1 mole of each substance. That's what they threw into the container, okay? And they want to know, at equilibrium, what would the concentrations be once all this stuff settles out, okay? So what we need to do is figure out, well, what's the change going to be? Well, we know that this is going to shift to the right. The equilibrium is going to shift that way. So what we're going to do, we're going to say all of these concentrations are going to increase by X amount. You're going to add X concentration to each one. So we're adding X. We don't know what X is yet. So if you add it to the product side, because that's how it's going to shift to the right, what would you do over here?
Subtract X.
Subtract it. So our change is going to be minus X and minus X. Okay? So here's our initial concentrations. Here's the change in X. Okay? And so now here we're going to write what's it going to look like at equilibrium. So at equilibrium, we're going to combine these two values. We're going to say 1 minus X. And
Wait, is the 1 mole our initial?
yeah, this is our, you're going to take your initial minus the change. And that's gonna be
Okay.
equilibrium. Okay. So 1 minus X, so your initial, and then you do whatever with the change. And so you'll say 1 minus X. You do that for the water as well. So it's 1 minus X. Over here on the product side, what's it going to look like for our CO2?
1 plus X.
Yep, 1 plus X, and then 1 plus X. Okay? So these are our equilibrium concentrations right there. That's our equilibrium concentrations. So now we're going to take what we know about the equilibrium. We know it's 5.10. At equilibrium, that's our constant. So we're going to write an expression, equilibrium expression with this information. Okay? So I'm going to write my equilibrium expression. I'm going to plug in 5.10 equals, okay? So 5.10, so that's my Kc, equals, and I'm going to put my products over my reactants. So I'm going to say, here's my products. I'm going to say 1 plus X times 1 plus, that's hard to do, 1 plus X. Divided by, and then you're going to do the reactants. 1 minus X times 1 minus X. Okay. Now let's.
So if there were coefficients,
Good
if
question.
there were coefficients in that, you would still make them exponents.
Yes, yes, you would. And if there were coefficients, like let's say that there was a 2 right here by this CO2, right here on the X, you would take your X times 2. So on the change, you would have to account for the coefficient there as well. So you would say like plus 2X or plus 3X, whatever the coefficient is. And then, yes, you apply it just like you would down here. You make it an exponent. All right, now at this point then, let's go ahead and see if we can do the math. Since you have 1 plus X times 1 plus X, how could we simplify that?
1 plus X squared.
1 plus X squared, yes, is right. So, and that's what I'm going to do. I'm going to rewrite this side and make it look like this. I'm going to say 1 plus X squared divided by 1 minus X squared. Okay, now all of you are math geniuses, okay? So, math geniuses, how could I simplify this whole problem real quick?
Cancel out the exponents.
Do what?
Square root of both sides.
Just cancel out the exponents.
If there was an exponent over here, yeah, probably that would work,
Just
but
Square root both
square root-
sides.
yeah, let's square root everything. So I'm going to square root this, and I'm going to square root that. I don't want those squares in there. So when you do that, I'm going to take the square root of 5.10, which is 2.26-ish. So I'm afraid that you're getting to where you can't see it. I'm going to erase this. So I'm going to say 2.26 is equal to 1 plus X over 1 minus X. Okay. And now we're just going to finish it out and do a little algebra, okay? I'm going to bring this bottom denominator up, and I'm going to multiply by both sides. So I'm going to say 2.26 minus 2.26x equals 1 plus x. Okay. All right. And now at this point, I'm just going to solve for x, right? So I'm going to add 2.26x to both sides. So it'll be 3.26x. And then what do I do with this 1 over here? What do I need to do with that? I'm going to subtract it. So I'm going to have 1.26. Okay. And then how do you solve for x now? So I have 1.26.
Just divide.
Divide it, right? I'm going to divide both sides by 3.26. So x equals, and then whatever that is,
0.8. So
Yeah.
3.9. 0.39 ish.
Yeah. So like 0.389-ish.
Well,
Wait,
that.
is that 2.26 minus 2.26x?
Yes, that's right.
Okay.
Yeah. So it should be somewhere around 0.387. And this is moles per liter or molarity. This is X, okay? Now listen, this is not the final answer, okay? What they were wanting to know was what are the concentrations at equilibrium, okay? So we're gonna go back to, because I erased mine, sorry. You're gonna go back to where you had your E, your equilibrium, and whatever it said to do. So like for the carbon monoxide, that was 1 minus X. So for our concentration of carbon monoxide, you're going to have to take 1 minus X, 3.87. So 1 minus 3.87.
0.613.
So 0.613. That's your concentration. That's your molarity at equilibrium of carbon monoxide. And you would do the same thing for H2O, which is going to be about the same value, 0.613. How about for like CO2 and H2 though? What about for carbon dioxide?
It would be 1.387.
Yeah, right. Very good. Because you're adding the X, right? So 1.387 for that one. And then same thing for your hydrogen gas. 1.387 is your concentration on that one. Okay. So this is a RICE formula or an ICE formula. You start with initial concentrations that are not at equilibrium. You have to figure out what would it do. Is it going to shift to the right? Is it going to shift to the left? Because that's going to determine if you add X's or you subtract them and on which side. Okay. And then you plug in the change, you plug in the C, and then you write your equilibrium values and plug it into that equilibrium expression. You're just putting everything together. Okay? So questions so far?
Do you want all this work on the doc, or would you rather just write it out on paper and then?
Oh, sweet mercy. Please don't try to do this stuff on Google Docs. If like yeah, that would be bad. Like
Good.
last night, I did all of mine in a notebook. So if I was going to do this for like a teacher, I would do it all in a notebook, take a picture, upload it. Yeah, this is too hard to type out. So,
Good.
hey, I do want us to try one more though. Hey, and listen, like when you go to college, if you go to chemistry and take a chemistry class, you will do equilibrium problems. There are some that involve using the quadratic formula, and I looked at those last night and I was like, nope, we're not doing that. Okay, just because like, I don't remember how to use the quadratic formula. You guys could probably do it because you're used to using it, but I don't remember how to do that. Just know that there are some that you would use the quadratic formula to solve, but we are not going to be doing those. Okay.
Hey, I gotta take a phone call from my mom, okay?
Go ahead. All right.
That
So,
was the creepiest.
and like whenever we're doing these video conferences, like feel free if you need to go take a call or if you need to step out, do what you gotta do. Okay.
Yes.
All right. So hey, we're gonna look at one more practice problem. It's the one. Let's see.
Hey, also, are all those problems due Friday, like the 2 through 56, like the even ones?
Yeah. And so what I would recommend doing is that you try to do, I think like last night, like if you do like, I think 7 or 8 a day, that will get them done. Like if you do try to get 8 of them done, like for the next 4 days, you'll get them done. And I know, listen, I know I put the answers on there. They're at the bottom. Like if you scroll to the bottom, the answers are on, and that's okay. I want you to check as you go. There's no sense in doing it if you're doing them all wrong. So check as you go, but what I'm going to be looking for is when you submit your work, is I'm looking for work.
Okay, I see where it is.
Your work. Okay. And then as you have questions, like we can do this again if you guys want to. We can try to do this again on Thursday and have like a chat, or I may just post on Google, like on my office hours. That's what Ms. Schaefer was doing today. She said, I think I'm just going to start posting that I'm here, and Google Hangouts works good too. Oh, I just put it on the screen. You guys see that? Yeah. Okay. Anyways, but Google Hangouts might be another option. Okay. All right. Hey, one more problem, and then we're going to call it quits for today. So I'm looking at, this is the last one, I think. It was practice problem number 4. It was sample exercise, I think, 13.11. Yep. Okay. So 13.11, that's where I am. That's what I'm going to start with. So if you want to read through that real quick. Okay.
My computer's being so slow.
You what?
My computer's being so slow.
Wow. Oh, yeah. It says your
Felt that.
bandwidth is low. Did you know that?
It what?
It says that your network bandwidth is low. That's the message that popped up on my screen just now. Just for you.
Oh,
All right.
that's awesome.
I would like to say this is the most paper I've used in like the last 4 months.
Awesome. Winner.
Hate it.
So you're forming hydrogen fluoride from hydrogen and fluorine. Okay. So this may be part of your problem is you're going to have to write these formulas out. I think the ones that I gave you on the practice today, they are already listed out. But if you're forming hydrogen fluoride gas, that's what you're making. And it's coming from hydrogen gas and fluorine gas. Here's our reaction, okay? Looks like that. H2 plus F2 yields HF, and I'm going to go ahead and balance that. So put a 2 right there. Okay, so if you read through this, what are some things that stick out? What's something we need to write down?
Equilibrium constant.
Yeah, our equilibrium constant. Our Kc is 1.15 times 10 to the second. It says, in a particular experiment, 3 moles of each component was added to a 1.5 liter flask, okay? And here's the thing. They don't give you actual molarity, but they give you all that you need to find it. So what do you need to do with the moles and the liters to find molarity? You remember?
Divided by how many liters there are.
Yeah, you take moles divided by liters. So you'll take 3 moles divided by 1.5, and that's going to be your starting concentration for everything. That's your initial concentration. So I'm going to take moles divided by liter. So I'll take 3 moles divided by 1.5 for each one. And so my initial concentration is going to be 2. It's a 2 molar solution. Okay, it's 2. Does everybody understand where I got 2? Yeah, 3 moles divided by 1.5, okay? All right, and then it says calculate equilibrium concentrations of all these species. Now here's the thing, what do we need to do first before we can proceed? What do we need to find out?
What that adds up to.
Dying.
Well, we need to find, like, we got to figure out, is this going to shift to the right or is it going to shift to the left? So what do we need to find?
Q.
We need to find the quotient.
Good,
Thank
our
you.
reaction quotient, good. Our reaction quotient, that's what we're going to try to. So to find Q, remember, to find Q, you just set up the expression like normal. So this is my concentration of my product. So I'm going to go 2. But I'm also going to square that, though, because of the coefficient.
1.
Okay. And then divided by my reactants, 2 times 2. Okay. So Q equals 1 because it's 4 divided by 4. So let me ask you, look at your K and your Q. How do they compare?
K is larger than Q.
K is larger than Q. So what's going to be favored?
Products.
The product.
So we're going to be adding to the product, adding stuff to the product. So we're going to add X here in a minute. Okay, here we go. So we've got our initial concentrations. Our initial concentrations just from the reading. So let's do our X. What's going to happen to the reactant side?
Minus X.
Yeah, we're going to minus it. Take away from this concentration. When this starts to happen, we're going to lose some of these reactants. Over here, we're going to add, but it's going to
2X.
be doubled, right? Good, very good. So plus 2X. All right. And then for our equilibrium, we're just going to write out what it looks like, okay? So it's going to be 2 minus X, 2 minus X, and then 2 plus 2X. 2 plus 2X. Okay? So here we go. Now we're going to write out our formula. And we're going to say, okay, we're going to write our expression. We're going to start with our value of Kc, which is 1.15 times 10 to the second equals, and then I'm going to come over here and I'm going to do, again, products over reactants. So I'm going to take this value right here, plus 2X, but don't forget, you had a coefficient, so we're going to have to square that. Okay? Divided by, and then we're going to do our reactants. We're going to say 2 minus X times 2 minus X. Okay, so 2 minus X times 2 minus X. I'm going to go ahead and just like make that be a square. I'm going to say 2 minus X squared. Okay. And again, real quickly, what could we do mathematically to make this be easier to solve?
Square root it.
Square root it, right? Let's square root both sides. Anytime you have those squares there, let's go ahead and square root this, and we'll square root this, okay? So if you do that, I got yesterday like 10.72.
Yeah.
Yeah. So 10.72 is equal to 2 plus 2X over minus X. And then you're just going to do your math and start to solve for X. You're going to bring this up here. And then once you do all that, once you do your algebra, because we're running out of time, I'm going to go ahead and finish this up. So once you do all your math, if you do it right, and I think I did mine right because it matched with what the book got, x should equal 1.53.
Yeah, got that.
Yeah, is that what you got? Holla.
Yeah.
Okay, so x should equal 1.53. Okay, x equals 1.53. Well, listen, is that what they're asking for? Is that what they want you to end with?
No.
No. You've got to take this value and you've got to plug it in where all those x's are because they want concentrations. They want to know what's the concentration of hydrogen gas. Well, it was minus x. So you'd take 2 minus 1.53 and it would give you 0.47. That was your equilibrium concentration. It was a 0.5 mole per liter. And then you do the same thing for the product side, okay? All right. Man, we ran through that. If you feel pretty good about these problems, so like these rice problems or these ice problems, they're towards the end of that little packet that I assigned today. If you want to go ahead and do those first and get those out of the way, you could, but it's like problems like 40, 44, 46, 50, 53, something like that. So, but just do your best, see how it goes. And if you have questions, like we can Google Hangout or just text me or email me or whatever, okay?
When are those problems due?
So the problems
Friday.
are not all due until Friday. Like you've got till Friday to finish the 2 through 56 evens.
So do you want us to put those on a doc?
I honestly, if you can, it's whatever is easiest for you. If it were me personally, I would write them out, take a picture, and submit the picture to Classroom.
Okay.
Because I hate trying to type out math equations on docs.
Okay.
So, but you do you. You
and
got
so-
all the time in the world.
And you can use ice for pressure as well, right?
Yes. Same thing applies for pressures. If they give you pressures, you can use the same ice method.
Okay, cool.
All right? Okay.
Good.
Enjoy your pandemic break. So,
Thank you.
Yay.
okay, bye, you guys.
Thanks for having us.
Bye.
Yeah, no problem. See you.
Bye.
Bye. Bye.